Hey everyone, welcome back to the Physics 30 Unit 2 videos. And in today's lesson, we're going to be continuing on our discussion with centripetal force. So in the first lesson, or I guess in the previous lesson, we had looked at what is centripetal force and how do we figure out that equation. And so in today's lesson, we're going to be looking at two specific cases. One where we have a horizontal system, and the second case is when we're working with just a vertical system. So we're going to start off with that horizontal system. So suppose you're driving on a road that follows a curve to the left on a flat road. As the car makes the turn, its speed remains constant and experiences that centripetal force. Remember, centripetal force meaning that inward pulling force. So the centripetal force is caused by the wheels turning to the left, continually changing the direction of the car. So if it weren't for the frictional force between the tire and the road, you actually wouldn't be able to turn. So this means that the frictional force between the tires and the road is the centripetal force. Alright, so let's put this into a bit of an equation form. So here we're saying that our frictional force is the centripetal force. So we can say that the centripetal force is equal to that frictional force. So that's between the tire and the road. So if you guys remember back to your previous lesson, so it was just the last video, and also to the very beginning of our unit, we actually have equations for our centripetal force and for the frictional force. So your centripetal force is your mass times your speed squared divided by your radius, and your frictional force was equal to mu, or the coefficient of friction, times the normal force. So your normal force, when we're working with a horizontal system, that means that we're not moving up or down. So that means that your normal force is equal to the gravitational force, or that force pulling downward. So we can also replace our normal force for the force of gravity equation. So you have your mass times your speed squared divided by your radius times is equal to, your coefficient of friction times, and the force due to gravity was equal to your mass times the acceleration due to gravity, which we let be g. So we can do one final step in order to simplify this equation, if you want to call this an equation. It's a little bit, lots of variables going everywhere, but it is a very useful equation. So what you guys can notice here is that we have mass on both sides of our equation. So if we were to divide by mass on each side, that would cancel out our mass. So our equation is going to be your speed squared divided by your radius is equal to the coefficient of friction times the force due to gravity. So here you guys can actually see that mass does not impact your overall system here when we're talking about that horizontal system. Alright, so let's do an example practicing this equation. So here we're going to determine the maximum speed at which a 1,500 kilogram car can round a curve that has a radius of 40.0 meters. If the coefficient of static friction, or your coefficient of friction, between the tires and the road is 0.60. So what we're going to do here first, as always, we're just going to write out our information. So here we're given that the mass of the car is 1,500 kilograms. Here we have the radius of the curve is 40.0 meters. And the coefficient of static friction is 0.60, which is mu. Remember, your coefficient of static friction does not have any units. And then, so just the last thing that we're looking for here is we're looking for that speed, so we're going to be looking for v. So here we know that we have, we're working with the horizontal system, so we can use that equation that we just came up with. So that is speed squared divided by your radius is equal to the coefficient of friction times the gravitational force. And once again, if you guys remember these gravitational force, I know it's not listed here in the question, but we know that to be 9.81 meters per second squared on Earth. right, so we can go ahead and plug in our plug in our values into the variables. So we have our speed squared divided by your radius, which is 40. Your coefficient of friction is 0.60, and we know that this gravitational force was 9.81. So what we want to do is we want to solve for our speed here. So we want to, first of all, get rid of this 40 that is underneath your speed. So if this one here is dividing your speed, to get rid of it, you want to multiply both sides. So what you're left with is speed squared is equal to, so it'll be 0.60 times 9.81 times 40.0, which you can actually plug all of this into your calculator. And you guys would find that your answer should give you 235.44. So now that we've done a calculation, I am going to make sure I keep track of sig figs. So this coefficient of friction has 2 sig figs. We don't consider this acceleration due to gravity. That's a value that we accept to be true. And then this one here has 3 sig figs. So overall, we have to go with the least amount of sig figs. So our answer there ultimately is going to have 2 sig figs. All right, so we're actually not done just yet. So here we have speed squared, but we want just our speed. So to get rid of a square, you're going to square root both sides. So if you plug that into your calculator, you should get a value of 15.3441. That's rounded, and we'll make sure to count for sig figs there. So our value here had 2 sig figs, so our answer here should have 2 sig figs. Meaning that our answer here is going to just be 15, and our units here are meters per second. So then to finish off this question, we are going to answer it with a sentence, and I'll just awkwardly put it down here. So the maximum speed of the car is 15 meters per second. All right, so now we're going to move on to the vertical system when we're talking about circular motion. All right, so all roller coasters, regardless of their appearance, are designed so that each car has sufficient velocity to remain in contact with the track at the top of the loop. At the top, the centripetal force is exerted by 2 forces. So there's the track of the car, which is your normal force, so that's pushing it outward, and then the force of gravity, which is pulling it down. So both forces push the car towards the center of the loop. So from the diagram above, we can actually see that the slowest any car can really go around the track is where your centripetal force is equal in size to the force of gravity. So that's looking at this example right in here. And so I guess if we would just want to quickly examine each of these cases, when we're looking at our, they give us some values here. So this one here is where our centripetal force is greater than the force of gravity. So here you can notice the track stays on the car. Well, that's really great. That's exactly what we want. Here, if you were to add these up, you would notice that your force, or your centripetal force, is equal to your force of gravity. Once again, here we're staying on the track. Life is great. This case, however, if we were to add these two up, we would see that our centripetal force is actually less than that gravitational force. And so this one here is where gravity is stronger than that centripetal force, and so the roller coaster would essentially fall off the track. And so that is definitely not what we would want in any kind of situation with a roller coaster. So it is important to understand how centripetal force works in, say, a vertical system. So just to recap that here, so the slowest that any car would be able to go is when your centripetal force is equal to the force of gravity. And so from this, we can actually come up with an equation. So we want our centripetal force to be equal to our gravity at the very least. We could have a higher centripetal force, but at the very least, these two values need to be equal. So just like what we did previously, we are going to substitute in some values here, your equations. So your centripetal force equation was mass times the speed squared divided by your radius. And your force of gravity was your mass times gravity. And just like last time, notice that we have our mass on each side of the equation, so we can divide by mass to get rid of it entirely in this equation that we've created. So we have our speed squared divided by your radius is equal to your gravity. So to make this just a little bit more useful, one thing that we can do is we can actually solve for our speed, which in itself is actually going to lead to one of your formulas on your departmental sheet. So if we want to solve for our speed, we first need to get rid of this radius. So here we're dividing by the radius, so to get rid of that, you need to multiply it on both sides. So then we have speed squared is equal to the force due to gravity, your acceleration due to gravity times that radius. Then we want just speed, so we have to get rid of this square. So we're going to square root both sides. So speed is equal to the square root of the acceleration due to gravity times your radius. And so as I had mentioned, this one here is a formula on your departmental sheet, but it's also a very useful one when we're looking at speed in terms of circular motion in a vertical system. So we're going to pick this up in the next video, and we will look at some examples practicing this equation. So I will see you guys in the next video.